In this section, we're going to talk about lattice energy. This is the energy that it takes to break apart a mole of particles in a lattice. Now, I think the conceptual aspects of this is far more important than the mathematical. As normal, we're going to do both, and we're going to talk about both, but focus more on the conceptual parts of this than the mathematical. So let's think about what we're going to be talking about here. Review a little bit of what we talked about with crystal structures, and think about what the idea of lattice energy would mean. For something like sodium chloride, this is going to be made of Na pluses and Cl minuses, and then it's going to be put in a structure that creates a lattice. Let's think about all of the energy values that we have that is required to get Na and Cl to bind in a lattice like this. Now I know that we haven't spent a lot of time talking about crystal structures. There's been a couple of different times you've probably seen it throughout chemistry and we've touched on it. We'll go into this in more detail later, but you don't need the details of the lattice in order to talk about the energy. So let's talk about what must happen to get sodium and chloride into a lattice. And this is as if we're talking about it from an energy standpoint, where we're starting from its elemental values or its standard state values. So sodium in its standard state is a solid. If we want to get it into this crystal structure, we're going to have to first turn it into a gas and then ionize it, and then allow those ions to attract each other. So that's 2 steps. And both of those are steps that we can find the energy for. We can go look those up in tables without a problem. Cl is a little different because in its standard state, Cl is already a gas, but it's a diatomic gas. It's a Cl2. And so we're going to need to half that Cl2 to get it into a Cl. And then it's already a gas, so that part's done. And then at that point, we need to ionize it and change it from a Cl, a monoatomic Cl, into its ion form, its Cl minus. And those are all values we can look up to or calculate. Now this last part is the lattice energy. The sodium plus and the Cl minus are then going to attract each other, and that forms your ionic compound. And that part of it is your lattice energy. That's the part that we're going to calculate and then talk about the concepts for. Now, all of these steps are energies that we can look up or calculate from tables. If we wanted, we could use these to solve for the lattice energy. The enthalpies of formation of the solid and the gaseous sodium would let us calculate the first step. So we could look up the enthalpies of formation and then do products minus reactants, just as we've been doing throughout, most of the chapter. Now, for chlorine, we can use the enthalpy of formations again to calculate the enthalpy of the monoatomic chlorine. And of course, you know the enthalpy of formation of Cl2, that's 0. So that part you could do as well. Now, we could also calculate what it would take to ionize these. In sodium's case, because you're taking it and turning it into a positive ion, it would be your ionization energy. You're removing an electron. So think back to 1A, and when you remove an electron, it's your ionization energy. For chlorine, when we ionize it, we're changing it into a negative, so it's attracting an electron. Think back to Chem 1A. If you attract an electron, it's electron affinity. So that's where that energy would come from. Now, all of these energies you can solve for. So the last one that we're kind of looking at now is our lattice energy, where the Na and the Cl are attracted to each other and they form NaCl. We can calculate this because we also know the energy of formation of NaCl. It's something we can go to a table and look up. In this case, I've given it to you, negative 411. Now we know all of these values together have to equal that negative 411. So all of the values have to add up to be our final H of formation, our negative 411. So in equation form, we're just saying, oh, if we add all of these up, H1, 2, 3, 4, and 5, we get our HF. Now there's only one of these that we don't know. The only one of these that we don't know is that H5, that lattice energy. So we can solve for that. Of course, you could do this any which way you wanted, fill in the numbers first, fill in the numbers last, whatever it is that you want to do. But you would take your delta HF, you would subtract your 108, you would subtract your 496, you would subtract your 122, You would subtract your negative 349, and then you would get your lattice energy. So in this case, when you do that, and type it into the calculator yourself to make sure you can get it, you would get a negative 788 kilojoules. So that's math behind it. As you can see, to be able to do it, I have to give you a huge amount of information, and then it's just subtraction. So it's good to be able to do. You should know how to do it. But the far more interesting thing comes up when we talk about how to do it conceptually, and the equation that actually describes the subtraction of the plus and the minus together. So conceptually, when you're comparing these, what we want to look at is Coulomb's law. Coulomb's law is what describes this attraction between ions, this plus and this minus attraction. So the Q's here are your charges on your ions. So those are your, let's say, your -1 and your +1, or your -2 and your +2. That's what's going to be based on the actual charges. The R that's right here is your separations of your ions. So this is going to describe how far apart your ions actually are from each other, or rather, it's based on the radius of your ions. So now that we have Coulomb's law, and I've told you what Q and R is, we can see how the lattice energy is very generally calculated. Coulomb's law is going to be telling us the energy of the attraction, and though we're never going to use this in terms of actual calculations, we can use it to talk about it conceptually. The Q1 and the Q2 value here are shown in the numerator, which means as the charge increases, the value increases. So as the charge increases, our lattice energy increases. Secondly, we have R. This is our separation. The larger the ions, the larger the R. So if R is increased, what's that going to do to our lattice energy? Let's take a second and look at that one. If our R is increased, our lattice energy is going to be decreased. So to quickly summarize what we just learned from Coulomb's law, as the charge of the ions go up, the lattice energy goes up. As the ion size increases, the lattice energy decreases. So now we're going to look at each one of these a little bit more carefully and do some examples. Remember when we talked about Coulomb's law, that the Q is the charge on the ions. The higher the charge, the higher the lattice energy. So in ionic compounds like sodium and fluoride, which have charges of 1 and -1, we're going to have a lower lattice energy than something like calcium and oxide, which has charges of 2 and -2. So here I gave you two different ionic compounds, one where each one has a charge of 1 and -1, and one where they have a charge of 2 and -2. And you can see what a huge difference in lattice energy is shown. And you can see that the NaCl is much, much smaller than the calcium oxide because of this difference in charge. Now, not always, but as a general rule, the charge is going to be more important than the ionic radius. So normally you want to look at the charges first, and that's going to tell you which one's going to be largest before you have to look at the radii. Now, what if all of the charges are the same? So for example, what if we had lithium chloride, sodium chloride, potassium chloride, and cesium chloride? All of the positive ions are +1, and all of the negative ions are -1, and are in fact the same species. So this is factored into the R in Coulomb's law, the separation of the ions. R is in the denominator here. So if you decrease R, you increase the lattice energy. So lithium chloride of this group is going to have the highest lattice energy, whereas something like cesium chloride is going to have the lowest lattice energy. Now, as I said before, usually ion charge is going to win out before this. But if they're all the same charges, then you can look at the radii. So let's do some examples. We're going to arrange these in order of increasing lattice energy. So the first thing we're going to look at is charge, because that has the biggest impact. So for lithium bromide, we have a +1 and a -1. For potassium iodide, we have a +1 and a -1. For calcium oxide, we have a +2 and a -2. Being able to do these charges is something that you should know from earlier classes. If you don't, make sure you either come in and get help or check out the videos where we cover that. I actually cover it in the naming videos. Now the one here that's automatically going to jump out at us as having the highest lattice energy is going to be your one with your highest charges. So for calcium oxide, we have +2, -2. This has your highest charge and should stand out to you as the one with the highest lattice energy because of it. For the next two, the lithium bromide and the potassium iodide, we need to look at the radius because they have the same charge. So the charges tell us it's going to be less than the calcium oxide, but the radius is going to tell us how those two compare with each other. So the lithium bromide is going to be not only your lowest charge, but it's also your lowest radius. The lithium and the bromide are smaller, which means that they're closer together. If they're smaller and they're closer together, they have a higher lattice energy because they're closer together. The charges are feeling each other more strongly. So when we look at this, our potassium iodide is going to be our smallest in terms of lattice energy because it is our lowest charge. And then of the two that we are comparing with the same charge, it is our largest species. So it goes potassium iodide because of its low charge and large radius. Lithium bromide because of its low charge and it's also small radius. And then calcium oxide based on its charge. We're not even really going to look at radius for that one. Let's do one more and see if you can do this one without my help. See if you can get this before listening to the podcast. Same idea as last time. We're going to be arranging these in increasing lattice energy. Here I have sodium chloride, magnesium chloride, and potassium chloride. Our charges on sodium chloride are a +1 and a -1. Our charge on magnesium chloride is a +2 for the magnesium and a -1 for the chlorine. And then for our potassium, we have a +1 and a -1. One of these should jump out as your highest lattice energy right away, and that's the one with your highest charge. So your magnesium chloride is going to be your highest charge. Now we need to look at the sodium and the potassium compared to each other. The chlorine's the same, which is nice. We don't even have to worry about the chlorine, but the sodium and the potassium we have to compare. Sodium is smaller than potassium in size. So because its radius is smaller, it's going to have a higher lattice energy than the potassium chloride. So I'll say that one more time. Because sodium's radius is smaller than potassium's, it's going to have a higher lattice energy. And so when we rank these, the potassium chloride is the lowest because it has the lowest charge, and then of the ones we're comparing, the highest radius. And then sodium chloride, and then magnesium chloride because of its charges. So doing a quick review, lattice energies are one part of the heat of formation of ionic compounds, so they can be calculated if you know all of the other values. Of course, you can also do the experiment in a calorimetry experiment to determine this as well. If you actually dissolve ionic species, you will change the temperature of the liquid that you're dissolving it in. The higher the charge, the higher the lattice energy. So something with a +2 -2 charge is going to be higher than something with a +2 +1 charge, +2 -1 charge. And that's going to be higher than something with a -1 +1 charge. The larger the radius, the smaller the lattice energy. So something that is very large in terms of its radius is going to have a smaller lattice energy because its separation value, its R value, is higher.